turned some stuff in with no name for chapter 2. That's always nifty. Let's see, 3, 2, 9, and 11, right? Put this up here. Oh, okay. I think somebody asked this question last time, if I remember correctly. So last time we learned 2 very important formulas. Can somebody tell me one of those formulas? Beautiful. What's that the formula for?
That's the formula for the arc length, right?
Arc length, I love it. So arc length is, so this question doesn't talk about arc length, but if it did, it would have given me, and you're fine, I didn't ask for this question, I just asked for 2 formulas. So one equation we learned last time was S equals arc theta, which tells me how far I would walk given an angle on the inside and a radius. If I walked along the circle, you guys with me?
Yes.
And the other one, of course, is the one relevant to this problem. Can somebody else tell me that one?
1/2 times r squared theta
Exactly. What's got to be true about theta?
is in radians.
Yes. So I try to make a big deal out of this. If theta is free in the world, it must be in radians. If theta is inside of a trig function, I don't give a shit what it can be a picture. At that point, I just need to know what kind of angle I'm asking the sine over the cosine of. If it's in the wild, it must be something physical, which is what radians are. So what do they tell me that I can shove into this formula?
You can put
What's the area?
area? Like with the
Yeah, what's the area? Did they tell me the area?
for
Yeah, 3 square units, so 3. What's the radius? 2. Can you solve for theta? That's really all that is. It's a little algebra thrown into our trig. Of course, there's going to be a lot of algebra in trig just because. Does that make sense? Then I can solve for the angle. You guys with me? Are you guys with me? What's up? So we have a formula. If I know the radius and the angle that I go through, I can tell this area of that piece of pie. This problem told me the area and the radius. If I know 2 of the 3 variables, I can solve for the third one, right? Using algebra. So that should be really, really, really easy to solve for theta. No worries.
so for problems 9 to 12, we would just use the other formula instead of the arc length one.
Yeah, number 11, for example, says find the measure in degrees of each central angle, right? So that one I would just, I would just find the radians and then convert it to degrees.
Okay.
Yeah, I can't remember if they give, I hope they don't. Thank God they don't. Because you could make this formula based on degrees and it would look horrible. There's no reason to do that. You guys kind of, so number 11 is exactly like number 9, except they want the answer in degrees, so I just do one extra step. I would just convert it to degrees. How do you convert radians to degrees?
Convert radians to degrees by doing
So if I had 11 radians, how do I make that into degrees? What do you want to get rid of? Radians, right?
yeah.
So rads would go down here, degrees would go up there. How many what's in which? 180 degrees in?
And 11? No.
No, of course not. No. 180 degrees in pi radians, right? The whole point is I don't know what the hell 11 is, right? So if you just put all that shit in your calculator, out it pops. You guys kind of with me? No? Normally when we go to degrees, we go ahead and divide. We make pi 3 point. We just do the pi button to get a decimal degrees. Are you guys at all with me? I guess all right. I know. It's been a weekend. I don't know what your weekends were like, right? You had a really good one, a really bad one. Sometimes that Monday you're like, I don't know what the hell happened last week. You guys doing okay? So remember the 2 formulas. S equals r theta. A equals 1/2 r squared theta. They are just formulas like any other formula in algebra. If I know enough of the other variables, I can solve for any other variable. You guys with me? Yes.
Can you go over number 5 on 3-1 and number 76?
3-1, number 5 first?
Number 10, I should say.
10.
5. Yes.
So this problem says each angle is an integer. When measured in radians, give the radian measure of the angle. Okay. So, if, all right, let me get rid of all this stuff. Hold on. So help me out. Let me do number 9, just because I am evil. Too bad. What is this? If I went this, what would that be? In radians. You can do it. You know it. You know this. One little thing. I went backwards, right? Negative pi. I love it. And what is pi roughly? No. And what is pi?
Oh, negative 3.14.
Blah, 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 right? So about negative 3.14.
Yeah.
The problem says the angle they give me is a integer. So what would your guess be for what angle this actually is? It's a little bit less than 3. It's a little less than negative 314 radians, right? And it's gotten, the answer has to be an integer, a whole number, or a negative. So the answer's got to be negative frickin' 3, right? It's just a little bit less than negative 3.14. I know the answer is a whole number or the negative of a whole number, negative 3. Does everybody understand the idea behind this problem now? Because the instructions might come out as very strange.
So okay, so I go to number 10, it would be like...
Real quick, what would this be?
90, or 270.
Negative pi over 2, is that cool? We all should, if I say pi over 2, you should kind of know it's 90. You've got to get more familiar with some of these radians versus degrees. What is pi? Again, pi is roughly 3.14, correct? Can somebody cut that in half for me? 1.07. Not quite. That would be 2.14. 1.57, 11. 1.5 to make it 3, and then the 07 to make it 14. So 1.5. You guys with me? So that would be negative 1.57. I don't know why I'm doing this problem for you. So if I go a little bit further, and I know the answer is a whole number or a negative whole number, what must the answer be? Negative 2. Yeah, I definitely didn't make it a negative 3. I'm definitely more than negative 1.5. So the answer's got to be negative 2. You guys see how that problem works? It's just trying to get you to start understanding how to tell where you are in a circle. If I said draw a 70-degree angle, you all could do that pretty well. If I said draw a 2.1 radian angle, that might, but this is trying to get you some practice to tell where some stuff is. You break it down to this is 3.14, this is 1.57, so if it was 2 point something, it's going to be in the middle. You guys kind of see what I'm saying? You always base it on what the main ones are. You can kind of guesstimate from there. Is that all right? I love you guys. You're all like, I don't know, man. Okay. Anything else from homework? Or if that wasn't sufficient, let me know. Yeah.
Number 76 from 3.1.
Okay. Did you have a question about this one?
No, it's a different section.
Okay. 70. Oh yeah, you said 76.
I just want to make sure I get it right.
So the instructions say just to find each function value. Okay. So right now, I almost would not understand you if you weren't first converting to degrees, right? Because right now, we have all this shit memorized with degrees. So sort of like when you learn a new language, when you learn some new vocabulary, it's understood that you're not going to be able to say a sentence just like I just did. You're going to say, the White House, that, you're going to be translating in your head. So I have no trouble if you convert 2 pi over 3 to degrees, because that's how everything's memorized. But in the process of doing that, you're going to start to remember what these things are. At the very least, remember what I told you? Anything over 3, if it's reduced and it's over 3, what's the reference angle? Does anyone remember? What is pi divided by 3? Pi thirds radians. How many degrees is that? 60. So anything that's reduced, that's over 3, is going to be related to 60 degrees. You guys with me? What is 3 pi over 3? Where's 3 pi over 3? Where is it? Yeah. 3 pi over 3 is a full pi, so it's going to be here. So where's 2 pi over 3?
120 degrees.
Yeah, you could go there, but you don't even need to go there. It's just going to be pi over 3 away from a full pi. Right? 3 pi over 3 is a full pi. 2 pi over 3 is pi over 3 away. There's your 60-degree reference angle. I know what quadrant it is. I actually never converted to degrees. I need you to understand. You know where pi is. Yeah? From your perspective there. Right? Over here. You with me?
Mm-hmm.
Okay. So therefore you know where 2 pi over 3 is, because this is 3 pi over 3, 2 pi over 3 is less. And you know it's over 3, so you know the reference angle is 60. You just got to figure out what quadrant you're in. What about over 4?
45.
Yeah. Over 4 is 45. What about like number 77? What would the reference angle be?
30.
30. I need you, are you guys with me at all? If it's over 6, it's some kind of 30 degrees. I just don't know which quadrant I'm in yet. Yes?
Would they ever give us any graphs that aren't on the table?
Say again?
Would they ever give us any graphs that aren't on the table?
That aren't on the...
Like, aren't on the table, they're not like perfect ones on the table.
Oh, not if they're supposed to be done by hand. I could give you problems and say use your calculator to determine what the cosine of 11 radians is, right? 11 radians is not related to any angle we're supposed to know anything about. You guys with me? Okay. But if I said, what is the cosine of 3 pi over 4, I don't want a decimal answer on that. No way in hell do I want a decimal answer on that. That's one you should be able to know, because it's a 45-degree angle. Are you guys with me? Are you guys with me? Okay. So, real quick, if I said, let's do this, and then I'll open it back up to questions, because I think, Brandon, you got a question. If I said, what is the cosine of 7 pi over 4? We already know what the reference angle is going to be in degrees. What's it going to be? 45. And again, be really careful. It's got to be reduced, right? But that's reduced. I can't reduce that anymore. So it's got to be some kind of 45. This is 0 in radians. What is this? Pi over 2. Pi. 3 pi over 2.
4 pi over 2 or
2 pi. I'm with you. I like that. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Exactly. 7 pi over 4 is just below 8 pi over 4. And what is 8 pi over 4? 2 pi. So 7 pi over 4 is just below 2 pi. Do you guys see that?
I always get confused with them.
Say again?
I always get confused, like say, like 5 pi over 3, or like,
All right,
or
real quick.
something like,
2 pi.
all these numbers.
2 pi. You ready?
Yeah.
Isn't this the same thing? If I multiply top divided by 3, isn't this 6 pi over 3? So wouldn't 5 pi over 3 be over here just pi over 3 away?
Yep.
So again, you can make pi and 2 pi over anything, because it's currently over 1. So 7 pi over 4, what is 2 pi in terms of fourths? What is multiply top divided by 4? 8 pi over 4. So where's 7 pi over 4? 1/4 of a pi away from 2 pi's. You can make either one of these over anything you want. So real quick, 2 pi over 1 is what over 6?
Oh, 12 pi over 6.
12 pi over 6. So where is 11 pi over 6? Almost all the way around, but just a little bit below 2 pi. It's pi over 6 away. The reference angle is 30 degrees. I got all my stuff. Maybe. How are you guys feeling? Are you guys all right? Does that make sense what I'm just asking? Because again, what was the whole idea of reference angle? Isn't it how much short or past I went the x-axis. So if this is a full pi, where's 5 pi over 4? Where is it? Isn't this just a little over 4 pi over 4? Isn't that this?
Yeah.
So isn't this equal to 4 pi over 4? You guys with me? So where's 5 pi over 4? Just past it. So that would be 5 pi over 4. The reference angle would be 45 degrees. Right? And then you can just do all your normal stuff. You know that sine and cosine are negative, blah, blah. You guys kind of with me? Yes?
Like all the rads that aren't in quadrant, you just supplement 180 for pi and solve it.
Of course, yeah, you totally could. What I'm trying to do up here is to get you to realize you don't need to. In fact, you need to start getting more used to just working with radians. I'm not going to claim that I can get you to the point where you're just as used to like 45 degrees as you are to pi over 4, but we're going to get much closer to that over time. So right now, if I gave you this problem and you went in and fully converted it to degrees, I'm not going to be like upset about that, but you really should try to not do that. You should try to do what I'm doing. The whole idea is, what quadrant did I end up in that tells me if it's positive or negative, whatever the question is? What's the reference angle? That's really the only two things I need to know, and I don't need to go to degrees to figure that out. Some of you guys are looking at me like, good for you, Jeff. But I said we don't need to do it. Okay. Sorry, yeah.
27, 3.2.
All right, so let's see. Madison, South Dakota, and Dallas, Texas are 1,200 kilometers apart, and they lie on the same north-south line. The latitude of Dallas is 33 degrees north. So what is the latitude of Madison? 11. So you got to draw this picture. Let's see.
Because I tried, you know, a bunch of different ways to do it, and it's just not.
Let me see. Oh, 1,200 kilometers apart, lie on the same north-south line. Dallas and what was it? Madison and Dallas. Okay, so Madison's up here. Dallas, Texas. 1,200 kilometers apart. The latitude of Dallas is 33 degrees north. So very quickly, I can't remember in this book, hopefully they do, or else this is really an evil question.
They do, but you're, like, I could solve for something like 23, but I can't solve for 27 because I don't know.
Well, don't you need the other degree to like in order to solve the problem?
Say again.
Don't you need the degree to solve the problem? Because I mean the only way you I mean I looked it up and it looks like Madison's just a higher degree than 33 degrees.
Oh, all right. Yeah, one thing you can do is double check the book and make sure it's actually, is that what they
For
say?
27, right? It's Madison.
Dallas is 33 degrees, it says.
And Madison, I looked it up on Google and it's higher than Dallas. Like, if you were to.
Of course, yeah, it's more north, that's true. But here, they explain to you, this example here is a really good one to have in mind as you do this problem, right? So, drawing it like that is not gonna help us all the way through, but I wanted to draw it the way that I thought that you guys might draw it when you first read through this. You gotta remember that we all lie on the surface of a curve, right? So when we do straight lines between things, they're not straight, correct? Unless you're a flat earther, and again, keep it to yourself. So the distance between the two is going to be this arc length, right? And here they describe to you how they measure the latitude degrees. Is with respect to, thankfully, the x-axis like we always do, in which case this is the equator, right? We're ignoring the tilt, we're just doing it based on, anyway, it doesn't have to worry about it. So it makes sense that if I put Dallas is here, so it's got to measure, what did it say again, 30, this is 33?
Yes.
And then Madison's up here, and we want to know what this angle is. But I know that this arc length, oh sorry, this arc length is 1,200 kilometers.
Okay, so it's not the radius, I thought it was the radius.
Oh, no. Yeah, the radius of the Earth is not 1,200 kilometers. Yeah,
Okay.
that'd be very tiny.
Yeah, it's like a lot bigger than that.
It'd be a lot quicker to get
Well,
somewhere.
then again, they make the math problems.
You're fine. Yeah. Is that better? So that's how you would draw this?
Yeah.
Okay.
Okay.
Okay. So, this is a good problem because I'm trying to figure out that angle. So let me call that angle theta, yeah? And then this would be, this is weird because it's really related to this angle here. You guys see what I'm saying? You guys see what I'm saying? If I wanted to do S equals R theta and plug 1,200 in, that would not be this theta. In fact, let me even call this, just to have it different from that, beta. Okay. Poor little beta angle. Stop for a minute. Do you see the issue? Why this is a true problem is because the angle I want to know is not directly related to either one of these. But if I call this angle beta, now we're getting somewhere. So it's all about how you draw the picture. So does that angle directly relate to this arc length?
Yeah.
Yes. If you solve for beta, how do you actually get what the latitude is?
Beta plus 33.
Beta plus 33. Yeah. All right, so I'm not going to say any more about that. I basically just told you exactly how to do the problem, so I figure that's where I should stop. Okay. Do that whenever you feel like it, John. Anything else from homework stuff?
45.
Same section? So let's see, this was where they talk about if your angle is very small. This is sort of like what I did, to prove the area formula. I assumed that was basically flat instead of an arc, right? And came up with the same formula. I don't know if you guys are with me at all, but and again, this is what I talked about last time. Why does it look like the Earth is flat? Because we're so close to the curve. If you get really close to a curve, it flattens out. You guys with me? And this Earth is a pretty damn big near circle. So when we're living on it, it's going to look flat. I like it, right? Do not look up YouTube flat Earth videos. They'll drive you a little crazy. Go to school, please. Let me see. So this one says, which one is it again? Sorry, 48? 5. Okay. The mass of a boat is 32 feet high. If it subtends an angle, and what subtends means, I can't remember if I've used that word yet. It's just if I walk along the surface, if I walk along a circle, the angle I subtend is just the angle that I kind of like went through. If somebody's standing at the center and they watch me walk, it's the angle they turn through. Is that cool? Subtend is just a quick way to say all of that. So if I move in a circular arc, it's the angle that I go through as I move. That's called subtended. The angle is what I subtended. Okay. If it subtends an angle of 2 degrees 11 minutes, how far away is it? Okay. So they kind of give you, let me see, I don't want to say this. So this is kind of cool for astronomy. Anybody at all into astronomy? Anybody like, yeah, okay, yeah, a little bit. So when you get into astronomy, it's really cool because you kind of take the latitude, longitude, and you sort of put it onto the sky, and then it becomes declination and so forth. So you can identify where stars are. So if I see 2 stars, I can tell how far apart they are. We normally talk about how far they are by the angle through which I move to go from one star to the other one. At least visually for us, right? How far apart they really are could be crazy far apart, right? So we talk about the angle that I go through to go from one thing to the other. So if I look at the moon, and I look at one side of the moon to the other side of the moon, I can describe its diameter in terms of an angular measure. What is the angle that I move through to get from one side of the moon to the other side of the moon? Are you guys at all with me? So here's the moon. Let me see. So weird when I put it where it goes. Alright, here we are on the Earth. I was going to draw it flat, but I didn't. Here's the moon. So if I look on this side of the moon and that side of the moon, one way to describe the distance, or in this case, the diameter, because the distance I move is the diameter of the moon, is through an angle. How big of an angle do I go through? If I look on that side and then I look to that side, how big of an angle do I actually have to move through? That is one way to describe how far things are apart or how wide things are in the sky. Is the angle that I go through. We stop for a minute. Does that make sense? So if there was a little thing over here, it's going to have a smaller angular measure for how wide and what the diameter is. You guys know what? And of course, if this sucker gets really close, if it's coming at me, once it's here, it's going to have a much bigger angular distance there. You guys kind of with me? So it's also about how far away it is. Okay, we stop for a minute. Did they give the, let's see. Okay, so here I've got, not the moon, I've got the mast of a boat. So I know the mast is 32 feet high, so that's this. And I also know that it subtends an angle of 2 degrees 11 minutes. So how would I draw that? So here's the mast of the boat. Here is the, so I know this is, where to go? 32 feet. And I know this angle is 2 degrees 11 minutes. So now they just want to know how far away it is, right?
Would I use tangent for that?
What is this again? What's the official name for this? Considering this is really curved a little bit, but we can assume it's not because the angle's so small. Oh, I see. No, I'm with you. But really, it's approximating the arc length, right?
Okay.
That's an approximation for the arc length, and the approximation gets better the smaller that angle is. It's sort of exactly like we're on the surface of the Earth, so it looks linear. It looks flat. Yes? Stop for a minute. What's the formula for arc length?
S equals R theta.
Do we know S?
Yeah, it's 32.
32. Do we know theta?
Yes.
Almost. Almost. What's wrong with this?
Not a degree.
It's not a radius. Okay, so convert, and then can't you throw that stuff in and solve for R? Okay, that's all. So that's how, if we have information about how, so we know how big the moon is. So I can tell how far away it is to the moon just by seeing what the angle is. So you all know that sometimes the moon is closer and sometimes it's further away. Are you guys with me? So if I just look at the angle across, I move, when it subtends, I can tell how far or how close the moon is. That's all I need to know, because we know how wide the moon is. We've been there. And again, if you're a flat earther, you probably don't believe that, so keep it to yourself. But we've been there. We know how wide the damn thing is. Yes?
So couldn't we also use a sine formula to solve for the length as well?
You gotta be careful. Is this a right triangle? No.
Maybe you're technically no, but if we're assuming that curve is flat.
You could, yeah, you could. If you want to, you totally could. You just don't need to. Does that make sense? Because you could, if I drop a line down the middle, I have made a right angle. Right? So I could just look at that if you want to. I'm just saying, this looks so much better. Right? Okay. Yeah.
And like, how do I put it? Can you tell me how I put 2 degrees and 11 minutes into the calculator and turn it into radians? Do I just?
Do we know how to change degrees to radians?
Yeah.
Yes.
Do I have purely degrees here?
No.
No. Do we know how to change degrees minutes to degrees?
Divide 11 by 60.
Second.
Divide the 11
Yeah. Change this to fully degrees, and then we know the process to go from degrees to radians.
Okay.
Yeah.
I just forgot.
You're good. I mean, does it make sense? Okay. 11 minutes will be 11 divided by 60 degrees, right? Okay.
And then you turn it into radians.
Then you just do the same thing, you know, multiply by pi, divide by 180, right? I like it. Of course you would, Jeff. Okay. You guys doing okay? Some of you guys look so beat up. I'm sorry. I'm a math teacher. I'm used to this.
I'm not
You know, beaten down, beaten up.
Crying.
All right. I'm sure some of you guys are still jet lagged from the change in the time. No? All right. Some of you guys are like, dude, I work until 6 a.m., so I'm always jet lagged. Okay, all right. So let's get into some new stuff. This is the new stuff. To be really honest, section 3.3 is nothing new. It's just using radians instead of degrees. So I gave you a handout that's actually got all this on it. So let me see. Anybody? It's got more, and the nice thing with the more is we're about to get into graphing trig functions anyway. So the more it's got is this graphing stuff. Anybody need the one that's got that on it? Just to remind you guys, one side is vectors. Don't look at that. Don't worry about the other side. Everybody else has got that? Oh. So real quick, this guy just, the only thing I care about with this, I am never going to make you fill in a blank unit circle. That's just bullshit. But that 1/2 right there, can anyone tell me what that has to do with trig? That 1/2 is right there. Yeah, so that's the cosine of 60 degrees. And of course, we already have that memorized, so that's not new information. The thing I want to give you this is to remind you, here's the radian translations, right? So you can kind of have this sit next to you as you're doing things just to help you get this in your head, what the radian translations are. You guys kind of wait for it. So all this section 3.3 really does, the only real thing it does is instead of working with degrees, we work with radians. So let's look at some of the homework just to show you what you're going to get. So number 7 is actually really old news. Number 7 has nothing to do with, this is kind of funny, it has nothing to do with radians or degrees. Could anyone tell me what the cosine of the angle is? Right, 2/2, yeah, so that's a unit circle. They tell me that that circle is a unit circle. So when it hits the unit circle, I could actually draw a line down, make a triangle. You guys with me? So the x piece would be the cosine, and the y piece is the sine. I like it. Does that work for any circle anywhere? Not quite. Remember, if it's a unit circle, those are exactly the cosine and the sine. If it's bigger or smaller, you got to be careful. The radius is not 1 anymore, so you can't use exactly the points that it hits. But this is a unit circle. We're golden. Just to show you guys at home what I'm talking about. That's that problem. Okay, so that problem is funny because it doesn't even involve radians. It's stuff we already know. So let's look at a different problem. We need to hire a camera person. Stay. So down here, they give us a radian measure, and they ask us to figure out what the sine, cosine, tangent are for them. Why is this really nice, this first one here?
Because you're given the radian.
Sure, but what is pi over 2? Yeah, pi over 2 radians is 90 degrees, right? So again, this is just getting you used to the radians, asking you the exact same questions asked you before, just before it was degrees. Now it's radians, right? Down here is an even more in your face example. I mean, now this one you got to be careful. This is what I was trying to get you ready for earlier. Can anyone tell me where 7 pi over 6, what quadrant that's in? I'm going to let you guys tell you. I get some third quadrants. Does that sound good? I get a fourth quadrant. I get another third quadrant. Yeah, where does the third quadrant start? Does that make sense? And pi, you guys with me? And what is pi? It's how many sixths? 6 pi over 6. So isn't 7 pi over 6 just a little bit past that?
Yeah.
Third quadrant. You guys with me?
Yes.
I like it. I like it a lot. And again, you could even do this. You could say, so again, this is 0. This is pi over 2. Good job, Jeff. This is pi. This is 3 pi over 2. And this is 2 pi. 7 pi over 6. This is 6 pi over 6. What is this over 6?
9 pi over 6.
9 pi over 6. So 7 pi over 6 is between them. So you know it's going to be in the third quadrant, right? You could do that for yourself. Does that make sense? You shouldn't have to. 7 pi over 6 is just a little smidge past pi, because it's just a little smidge past 6 pi over 6, right? So I know it should be in the third quadrant. In fact, what's the reference angle in degrees? 30. You knew that from the beginning because it's over 6 and it's reduced. Yes?
So in a way, you're saying to, like, the way to more easily be able to see which quadrant is to, like, divide, like, put a number over a number in order to get a sense of, like, where.
Yeah, relative to the fraction I'm looking at.
Right,
If I look at pi, it's not as easy. But if I look at 6 pi over 6, which is the same as pi, now 7 pi over 6 is easy to tell where it is, right? Does that make sense? So you can make any of these damn things. They're currently over 1. This is over 2. But you can make them whatever, so you can compare easier, right? Okay. So is that all right? You guys all right? Okay. Where would, what do you got, Jeff? Where would, you can do it, buddy. Where would 13 pi over 6 be? Because 2 pi would be 12 pi over 6.
Yeah.
So 13 pi over 6 would actually go a little bit past that. So I'd just be in the first quadrant. You guys with me?
And would it be 30 degrees?
Again, yeah, it's over 6. It's reduced. So I keep saying reduced because if I said, what you got, Jeff? You could do it 12, I don't know. Let's say you 9 pi over 6. That is not a 30-degree reference angle. Because what can I do? Reduce it. What does it reduce to?
3 over 2.
3 pi over 2. That is just this here, right? Not a 30-degree reference angle. You with me? So it's got to be reduced to do the little shortcut. But if it's reduced, it kicks so much ass. You hopefully some of you guys. It sounds like some of you guys are there. Pi over 6, 30. Pi over 4, 45. Pi over 3, 60. Right? So you know over 3 is going to be compared to 60 as long as it's reduced. Over 6 is going to be 30 as long as it's blah, 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 blah. Okay, I love you guys. All right. Let me see. Just make sure there's nothing too freaky in here. There's a bunch of calculator stuff. What do you do? This one's kind of nifty. Okay, this one I like, and of course I would. Let me zoom in on this thing. I don't know. I watch too many horror movies. I think Pinhead when I see this, but you can zoom. Nope, I'm zoomed in as much as I can. Focus. Okay. This one's kind of nifty. So watch this. Watch this. Okay. 0.2 radians is right there. Oh God. So if I want to see an estimate for what the cosine is, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, I'd say like 0.96 would be an estimate for what the cosine is. Can somebody please, in your calculator, make sure you're in radians? Can you do cosine of 0.2? Make sure you're in radians or else things get freaky. Cosine of 0.2, 0.98.
Yeah, 0.98.
So 0.96 is a decent, by eye estimate for a human. So this is kind of cool because it's really putting it in your face that it literally is. If I want to know the cosine of 0.4, 0.6, 0.7, 0.8, it's just a little bit above 0.9. So somebody help me out, what is the cosine of 0.4?
0.92.
A little bit above 0.9. Sine would be a little bit below 0.4. What's the sine of 0.4? Should be like 0.37 or something.
389.
What is it?
389.
389, okay, good. Just a little bit below 0.4. You guys? So again, I know we got calculators, but this kind of problem, I love this kind of problem because it's reminding you the cosine and sine are literally just how long each freaking side is in a unit circle. So this is a unit circle. It's got a radius of 1, right? You guys kind of with me? And therefore, if I just can see how long this side is, that's the sine. How long is this side? That's the cosine. That's kind of awesome. Reminding ourselves we're the humans here. We can get pretty close without a calculator, damn it. Okay, maybe. You guys still with me? I don't know if you guys appreciate that problem as much as I do, but we'll find out. Okay. I think I'm making the point that this section does not have a lot of new stuff. Yes.
Something like, say 69 and 72 looks off.
So you find the exact value of s
And 75.
in the given interval that has a given circular function value. Sorry? So look at 67 for a second.
Yeah.
What quadrant am I in? Starts at pi over 2, goes to pi. 90 to 180, that's the second quadrant, correct?
Yeah.
And why does it make sense it's the second quadrant? Because that's one of the quadrants where sign is positive. Are you with me? Yes?
Yes.
Go ahead, sorry.
I had a question about like the last one we did where it's like the trig functions of like radians.
All right, give me a second. I'll go right back to it. The one with the picture, the thing? This one.
No. The one before that where we were showing like.
Oh, before that. Okay, give me a second. Okay, we'll go back. What's the reference angle that makes sine 1/2? What's the reference angle that makes sine 1/2? 30. What's that in terms of radians? Pi over 6. Keep gas. So it's 30-degree reference angle, which is pi over 6 radians. But I'm supposed to be in this quadrant, correct? So I stop short of pi by pi over 6. So of course, what angle is that then? If I'm 1/6 of a pi short of a full pi, which is a really weird math insult, but that's okay. That guy's 1/6 of a pi short. Huh?
150 degrees.
Don't give me degrees. I don't care about degrees. I want radians. 1/6 of a pi short of a full pi is how much of a pi? 5 pi over 6. You guys with me? 5 pi over 6. So that's the whole idea of this problem is they tell you what quadrant you're in. They tell you a value you're supposed to know the angle for. You just got to make sure it ends up in radians, in the right quadrant. So whenever we do this, if I just ask you when is tangent -1, what reference angle would tangent be -1? What reference angle is tangent some kind of 1? What is tangent? 1 over what?
Y over X.
Which is sine over cosine, correct?
Yeah.
So when is tangent going to be 1? When sine and cosine are the same? What angle are they the same at? Okay, so try to see. So if I tell you the tangent is -1, the reference angle is going to be, which is also known as what degree? Radians. 45 is what? How many radians? Pi over 4. So I know the reference angle is pi over 4. Look at number 71. That's the one I'm talking about now. Reference angle is pi over 4. Tangent is -1, so I know it's going to be 45 degrees. That's pi over 4. I'm in this quadrant, which makes sense because in the fourth quadrant, tangent is negative. I'm pi over 4 short of 2 pi. Well, what's 2 pi? How many fourths? 8 pi over 4. I'm 1/4 shy of that. 7 pi over 4. Done. Next problem, please. You guys, again, the important thing is the steps I took and why I took them. If I just tell you cosine of some angle is rad 3 over 2, you should be able to tell me what the shit the reference angle is. Yes? What cosine is rad 3 over 2? Cosine of what?
60.
Rad 3 over 2, cosine. Cosine's big when it's close to 30 degrees, which is what in radians? Pi over 6. And then if I tell you the quadrant, you should be able to figure out pi over 6 away from the x-axis. Are you guys all with me?
Would it be different for the squared ones?
Say again?
Would it be different for the squared ones? Like,
Squared
this
ones.
is not a part of the problem, but like 76, for example, you have something squared. Do you take the square root and then
Hold
solve?
on, we'll get there. Yeah, this one's a cool one. I like it. Of course, I would like this one. So when I take a square root, what do you get when you take a square root? Why do I have to square root it? Because I only know angles based on like tangent code, not tangent squared. We don't have all that memorized, thankfully. What do I get when I take the square root? Got to be careful. Is it just this? Whenever I put a square root, what do I have to put down?
Oh, plus and minus.
Plus or minus. So I'm going to get a lot of possibilities, but they tell me it's anywhere from 0 to 2 pi. Do you guys know, let's see how much you know tangent. All right. You all should know sine and cosine by now, right? In fact, we already did the test in the quiz a while. You all should know if I said, what sine is 60, you might take about 3 seconds, and you should tell me, right? Tangent, maybe not as much. But I gave you a little clue. What's on the top of tangent? Sine. Tangent goes like sine. When is sine bigger? 30 or 60 degrees? 60. I love it. You with me? So tangent will be bigger at 60 degrees versus 30. Tangent could be either 1 at 45 degrees, or what? What are the other two main things tangent could be? You guys remember? It could be rad 3, or it could be rad 3 over 3. No, we don't like this. Okay. All right. Let's focus on this for a minute. I'm going to assume that it's true what I said earlier about everybody knows sine and cosine. Because if you don't, you got to come see me. Good Lord. You should all know it. But tangent, I really didn't make you memorize tangent. You can if you want to. Like some of you guys might want to, but I don't want to. So what I realized is, since tangent goes like sine, because sine is on the top. So when sine gets really big, let me ask you this. When sine gets bigger, what's cosine doing? It's smaller. So when sine gets bigger and cosine gets smaller, doesn't this whole thing get big? Top's getting bigger, I'm dividing by less, that gets even bigger. So when sine is big, tangent is big. When sine is small, cosine's big, this whole thing is small. So when sine is small, tangent is small. So all I need to remember is tangent, the main things tangent can be are 1, rad 3 over 3, 0, undefined. Those are the things it could be at the angles we have memorized. Can anyone tell me when tangent is undefined? What angle would tangent be undefined?
90? Or pi over 2?
What's on the bottom of tangent? Cosine. Undefined means can't exist. I can't divide by 0. Cosine is 0 at 90 or 270. Pi over 2 or 3 pi over 2 radians, yes? You guys kind of with me? Okay. So what's more interesting is these three. This one should be easy. Tangent being a ratio of sine and cosine. When are sine and cosine the same? When it's exactly halfway between the x and y axes, 45 degrees. That's easy. These two are the ones that need to be differentiated. That's going to be when you're some kind of 60 degrees, because of course tangent is bigger when sine is bigger. Do you all agree that rad 3 divided by 3 is smaller than rad 3? Cool. So this is going to be at 30 degrees. So what's nifty then about this problem? When you take a square root, you get plus or minus. What reference angle are we talking about? 60, because that's when it's bigger. Positive, negative. Isn't that, isn't that every single quadrant?
Yeah.
Just a 60-degree reference angle? Yes? Or better yet, what's 60? It's pi over 3. So just the pi over 3 reference angle. So what angle is this then? To here. If that's pi over 3 short. 2 pi over 3. I love it. Keep going. You guys kind of see that. So whenever you have a squared trig function equals a value, that's going to open the door to more possibilities because it could be positive or negative. Right? What do you square to get 9?
3.
Or?
-3.
Alright, so whenever you have a squared function equals a number, that gives you so many more possibilities because it could be positive or negative. Okay, maybe. Some of you guys are leaning in like, this guy's going to start making sense any day. Yeah.
So for this problem, number 76, the answer is, would be tangent of s equals plus or minus.
Yeah, so S will be all the pi over 3 reference angles. You just got to figure them out. We've got pi over 3, we got 2 pi over 3. Keep going. Well, 3 pi over 3, careful. What's 3 pi over 3?
That'd be pi.
That'd be pi. It's not a part of the answer. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And then 6 pi over 3 is back to 0, correct? You guys kind of with me?
So there's more than one answer to that problem.
Oh, hell yeah.
Oh, gotcha. I know you this one.
Bless you. Especially because, look, they made it open. So even like number 74, it's not squared, correct?
So,
But there's more than one answer because it's 0 to 2 pi. That's all the quadrants. How many places is cosine negative? How many quadrants? How many quadrants is cosine negative? Which ones?
Second and third.
Second and third. So I should get 2 answers number 74, for example, right?
okay.
Because there's 2 places it could be negative. Why was the other earlier problem easier? Because they only allowed me to look at 1 quadrant at a time. See that? Sound a little bit like Christopher Wall. 1 quadrant.
At a time.
Alright, sorry guys. Y'all like, whatever, man. Math boy. Okay. Alright. Those still aren't new information. This is still based on the things we should have memorized. I understand this section will be a little more difficult because it adds in the extra step of radians. But I need you to understand it's nothing new. It's just I gotta translate now. Between what I know in degrees and what I need to know in radians. Okay. And you're welcome, we're not gonna do section 3-4. That's nothing new. On your homework sheet, you see we're not supposed to do it anyway. So, yes, sorry.
When you use trig function with radians, could you just put in, like, let's say you're using 10, 9 pi over 10, could you then, or 5 pi over 4, could you just use the reference angle as in sine pi over 4 and then cosine pi over 4, or does that not work?
Alright, come at me again. So the question would be tangent of
5 pi over 4.
5 pi over 4?
And then, would you do like sine over 5 pi over 4, or would you just sine pi over 4 over cosine pi over 4?
Yeah, that's a pretty good first step. What quadrant am I in?
Second or third.
They're all over the place. I heard the right answer, and then I heard a few wrong answers. I'm in the third quadrant, yeah? I'm a little past pi. You guys all with me? You with me?
Oh, yeah.
Oh, yeah.
Alright. Now real quick, isn't sine in quadrant 3 negative? Do you see how I did this? What's the reference angle? Pi over 4, and it's negative. But cosine is also negative. So those cancel, right? So this is one way to put together tangent. You don't have to memorize tangents separate. You can just kind of break it down into sine and cosine, and you got those memorized, right? Now me, I wouldn't do any of this shit. In fact, you shouldn't either, because what's the reference angle in degrees? 45. Tangent of 45 is some kind of 1. Do you understand what I mean by some kind of 1? Negative 1 or positive 1. I'm in the third quadrant. Sine, cosine are both negative, so it should be positive 1. I'm done. And again, that's just because you know the shortcut. I told you, if it's over 4 reduced, 45-degree reference angle, then I just worry what quadrant am I in, and then I should have the answer. All I got to know is what quadrant I'm in, yeah? 5 pi over 4 is a little more than a full pi, so I'm in the third quadrant. Bam. Maybe. I love it. I love you guys. You're all like, this is too much for a Monday morning. Too bad. All right. Okay. So again, I don't think there's too much new stuff in section 3.3 at all. You got to get in there and tell me if you agree. A few of you guys have already gotten in there. So what I want to focus the rest of my little amount of time I've got left is we're going to get into graphing. And I gave you this handout, and at the bottom it's got some of the basic graphs. Of course, we're going to do more than just the basic graphs. So let's do this. Anytime I hit a function that I don't know what the graph looks like, what do we do in algebra to figure that out? We create the magnificent table of values, right? XY table, for example, right? So let's say I've got let's see. I don't know which way you guys prefer. I'm going to try this. I'm going to change to the projector, just because you're surrounded by screens. See how this goes. Poor little thing. Okay, oh, there you go. Okay, so, yeah.
So on the paper it says, for the next period, like 2 pi or pi. What does period mean in terms of graph?
We're getting there. Yeah, I told you. On that paper, there was stuff in our future that's still in our future. Okay. If I say that a trig function is periodic, and this is related to your question. All right, I don't know what you're doing. You're going a little crazy. Can you zoom out, please? There we go. Thank you. Okay, there you go. It's got a little bit of a stutter. It's okay. What is weird about trig values? Why do we only have to memorize the first quadrant? Because whatever values are there, what do they do?
They repeat.
Repeat. Beautiful. So periodic functions are any function that has a certain set number of values that it then repeats forever. Right? So there are other periodic functions in existence, but the ones we're obviously focused on are the trigonometric functions, and they are all periodic. They just repeat the damn values forever. They go a little insane. Poor little dudes. So let's focus on sine, our most basic one, the first one we worked with ever. Let's just focus on sine. So let's say that I have this function, sine x. Let's throw some values in there. Let's use radians, just because I'm evil. 0, pi over 6, pi over 4, pi over 3, pi over 2. We'll start with these. All right. So this we should all know. What's the sine of 0? 0. Sine of pi over 6? 1/2 starts to grow a little bit, right? Pi over 4? Grows a little more. Pi over 3? Grows a little more. Pi over 2? 1 grows a little more, right? Is everybody with me? Old news. And again, I know the radians are relatively new, but we should be at a place now where we kind of can convert a little bit quickly. Now, one thing you'd use as a reference to kind of keep yourself straight is these. When we get into graphing, this could be very useful. So now I'm going to go a reference angle of pi over 3, a reference angle of pi over 4, a reference angle of pi over 6, and then pi. Now here's the nice thing. You don't have to think too much about this because sine starts at 0. You see from your perspective, starts at 0, it grows, and then of course once it gets to 1, after that what's it going to do? Sorry?
No, just like, just doing what you're doing.
Yeah? Oh, I'm sorry. Once it gets to 1, it's going to do what? Is it going to grow more?
No.
No, now it's going to go back down exactly through all the same shit it just did. Which is, again, part of the periodic nature. So then it's going to go rad 3 over 2, rad 2 over 2, 1/2, 0. So we've never looked at sine exactly like this before. What's it going to do now? And again, you could use this as a reference, keep yourself straight, blah, blah, blah. So now I'm going to have 7 pi over 6, 4 pi over, no, 3 pi over 4. No, Jeff, 5 pi over 4. Become a thing. 4 pi over 3, and then 3 pi over 2. Now, when you make everything fractions, things are not immediately intuitive, ever. Shit, I'm sorry, guys. Remind me when to leave stuff up here. Okay. Now that we're looking at it like this, what's it going to do? What quadrant am I in now?
3.
Quadrant 3. So it's going to build again, but it's going to go negative. So again, it starts to build up again. Negative 1/2. Negative rad 2 over 2. Negative rad 3 over 2. Negative 1. And of course, from there, it's going to go back down. Okay, I think we can get the idea. But now I can graph this. We haven't done this yet. This is just a function. It's a freaky function. It's based on ratios of sides of right triangles, but who cares? It's a function with inputs and outputs. So I can graph this thing. I need more room. You can do it, Jeff. There you go, down there. Okay. So let's see what we can do. We can do, let me do this first. So we got pi over 2, pi, 3 pi over 2, 2 pi. And then I can put in there pi over 4, 3 pi over 4, 4 pi, 5 pi over 4, 6 pi over 4, 7 pi over 4. All right. Okay, these are the main ones. So I have more information here than I really need. I'm going to use it a little bit. So on one level, this is nothing different from plotting y equals x squared plus 7x. Right? You make an xy table, get the and you put the thing on there. So part of what we got to learn is what do these things look like? And if I know what they look like, I need less points to graph them. Because I already have the shape. I just got to put the points in and fill the shape in. So what's the highest the output could be? For a sine function, what's the biggest number that I can get out? 1. What's the smallest number I can get out? Negative 1. That's crazy. So I'll put 0.5 here. Negative 0.5. Okay. So let's see if we can plot some of this stuff going on. So 0, 0, bam! Start off strong. That's the chorus. Come in strong in the chorus. Pi over 4 is rad 2 over 2. Rad 2 is roughly 1.4. Divide that by 2, I get 0.7. So if you ever have to plot a function by hand, you're going to round a lot, because I'm not going to be able to do exactly. Right? So 0.7 is pretty damn, that's about it. That's as much as I can do. So 0.7 is going to be just a little below halfway here. You guys with me? Pi over 6 would be down here somewhere, and its output would be 1/2. You guys semi with me? All I'm doing is plotting the points now, right? But you can see why I don't need the over 6 as much. The over 4 is going to be enough to fill this in, hopefully. Pi over 3 would be between these two, and it would be rad 3 over 2, and I always forget what rad 3 is. Can somebody do that in the calculator real quick? I think it's
1.6.
What is it?
It's 1.6 something.
Well, I thought it was 1.7 something, but
1.7.
I always forget.
1.7.
yeah. Here, Jeff. You're going to finally remember this.
1.73.
Yeah, thank you. 1.73. Get that in your head, Jeff. Divided by 2, 0.9 roughly. You with me? So here it goes up to 0.9, and then at pi over 2, it's 1. All right, sorry. So can you agree with me that I really don't need some of this information. If I just do the over 4s, I can get that. You guys see that? But again, it does still go through all of the points, make it big. Yes?
Couldn't you just keep like the major points like pi over 2?
Exactly what I mean. That's exactly what I'm trying to say. I wanted to plot a few of the over 6s, over 3s, and you all agree I don't really need them. I can see the shape of this curve without them, but I just wanted to put them once. Now let's focus on the main ones. 3 pi over 4. 3 pi over 4. So it's 0.7 again, roughly, right? So 0.7 we said is about right here. And then pi is 0. So far we got that. So far it looks like a parabola, right? A parabola. But of course it's got a floor. It's got a ceiling and a floor, yes? Okay. 5 pi over 4. Every single time I get a 45-degree angle, I know it's right over 2, and we now know that is roughly 0.7. Is that cool? So every time I hit a pi over 4, it's some kind of 0.7. Now it's going to be negative 0.7, which is about right there. 3 pi over 2 is when sine is really the biggest negative. 7 pi over 4 is right across from that one, because it's another 45-degree reference angle. Am I going too fast, or am I doing okay? You guys all right? It's all the same stuff, just negative now. Whee! Oh, God, Jeff. So it's just going to continue this for frickin' ever, right? Because, again, the fact that this goes forever is related to the fact that you just keep going around the damn circle as much as you want to. You guys with me? At all with me? You guys with me? Or are you against me?
No.
Okay. Alright, so, and one thing I try to, what really doesn't make sense to a student possibly, and I remember kind of being confused about this too, is why the shit do we just keep going around this damn circle? Right? Well, one reason is if I add in a third dimension. Couldn't I go around a circle but also at the same time just keep going up a little bit each time? So from above, it just looks like I'm doing this. From the side, I'm going up this thing. So I always think about those parking garage exits sometimes, and you gotta get around there. You guys got it with me?
Actually, from the side, kind of looks like you're going.
Oh yeah, from the side, because when you're coming at me, yeah, you can't really see it. Yeah, so it looks like you're going like this. Yeah, exactly. From above, it totally looks like you're just going in a circle. I love it. So when we add in another dimension, we do want the ability to continue going around the circle. I understand in 2 dimensions it seems a little bit repetitive, but we need the fuller picture. Okay, maybe. Yes.
I remember when I took math in 76 first and I had Miss Willover saying some like really crazy shit about 4th dimension,
Oh yeah.
and that just kind of broke my head.
I'm not going to take us to the 4th dimension. Don't worry. The only place. Okay. No need for the 4th dimension really to make sense of this. Let me think. There was something else I wanted to say. Oh, do you all agree with me that we have plotted enough points? If I wanted to continue, wouldn't I just repeat all the same outputs?
Yeah.
Do you all agree that if I stopped at pi, that would not have been enough? Because I wouldn't have picked up the negative ones, right?
Yeah.
We give this a name. This, what I've graphed for the most part, except for these outer, and you can do it, Jeff, arrows. This part in the middle, this part right here, we call that one cycle.
Is that the same thing as a period?
So again,
Is that the same as a period?
a cycle is this shape. A period is how long it takes to make that shape. So how one cycle fit in how long? How long did it take me to make one cycle? 2 pi. You guys with me? The period of this is 2 pi because that is how long it takes to make one cycle. Why would it ever not be 2 pi? Can you imagine? And again, what physical thing, I keep pointing there, I'm sorry. What physical thing does that represent? Does anyone know? Give me an example of what a sine wave might represent. Does anyone know? Sound wave.
Yeah.
Can anyone imitate a car going past you? Yeah. Does anyone know what that effect is called? Doppler effect. So you got Doppler radar that uses that again. Doppler effect just means that it's coming towards you, the sound waves are compressed. Because the sound source is coming at you. So when I compress the sound wave, wouldn't it take less than 2 pi if I compressed it? Just like a spring. I could take this thing and I could just go, and I could make the period pi. So it would go, and it would go through one cycle in 1 pi. You guys kind of with me? This is one reason why we want to identify the period, is because it depends on the physical situation about how long does it take for this to go through.
This also basically means like a revolution.
Say again?
Like a revolution, you're saying like how before, like almost like a sphere or circle.
Yeah, so the period relates to the time it takes to get around the circle. So you can imagine somebody going around the circle like this, oh, and then somebody else going, oh, yeah. So that would relate to, and again, sound-wise, it would relate to the pitch, the frequency.
But would the cycle be like toward revolution?
Oh, yeah, good. So I love it. So one cycle, in this case, for a trig function, is related to one complete revolution around this, right? Now, for sine and cosine, let me be careful. We'll see what tangent. Tangent's a little bit different. We'll see why when we get there. Okay, how are we doing so far? So sine looks like this. What's the important thing for sine? Where does the, let me see, what do I want to call this? Where does the base cycle, this base cycle, where does it start? At 0, the sine is 0. You with me? How is cosine going to be different? What is the cosine of 0? 1. So when I draw cosine, it's not going to have a y-intercept of 0. It's going to have a y-intercept of 1. So can you imagine all it really is going to do is it's going to push this back? So it's going to start at 1, and then it's going to go through. So let's see what it's going to do. Let's see if we can do this without doing too much craziness. So here's what a cosine is going to do. Now that we know the basic shape of the sine and cosine is this. Just forever. Right? That's the shape. Okay. So now we can be a little less precise with the points we use because we know the shape. So if I wanted to graph a cosine function, or at least one cycle of a cosine function, like you just told me it starts at 1, yes? Cosine loves it on the x-axis. 0 degrees is all x-axis. Or 0 radians for that matter. Let's just put the main players in here. Of course, the more you know the shape of a function, the less inputs you need to use. So at pi over 2, what is cosine? What's cosine at 90 degrees? Is it like it there? 0. Hates that shit, so it's 0. Cosine of pi. Kind of gave it away there, but go down a little bit deeper. -1, is that cool? Cosine of 3 pi over 2? 0 again, it's a 90 degree. It doesn't like it on the y-axis. 2 pi? 1. So cosine looks like this. You can make whatever sound effects you like. Again, truly it looks the same as sine, because if I kept going, I could define a cycle to be here. Do you guys see that? But very often we consider cosine to be this. The main thing about cosine different from sine is it starts at its maximum instead of at its midline. Let me say that word again. Midline. On both of these graphs, where's the midline? 0. How would I make the midline different? Move it up or down, correct? Do you guys remember what to do to this function to make it move up? If I took cosine x and I wanted to move it up 1, I would just say +1. That would be the same exact shape, just with a midline at 1. So now it would do this thing around 1. I did that horribly, but it was just a quick sketch. Are you guys with me? So I don't know how many of you guys have ever worked with transformations of functions. So I take a parabola and then I move it over to.
Yep.
What does that do to the function? It would be the question, right? So we're going to have to focus on that. Holy shit. Time flies in this place. So next time we're going to focus on transformations of functions, so then we can do transformations of trig. We're gonna squish them, we're gonna stretch them, we're gonna move them up and down, four little things. Okay.
Okay, don't stretch them too much, you might tear the muscles.
Huh?
Don't stretch them too much, you might hurt the muscles.
Exactly.
So,
Just a little pre-workout stretch.
sine of x plus one, would it be like similar to cosine of x?
No, it wouldn't be. To make cosine the same as sine, you'd actually have to do 90 minus x. You have to shift it by 9 degrees. And we know that already, right? Yeah. So we're gonna talk next time also about when we start talking about function transformations, I'm gonna bring that back identity. Sine of x equals cosine of 90 minus x, right? I'm gonna see what it means visually.
Yeah, and when you said plus one, like, what did that do?
It just lifts the whole graph up by 1.